Hello, everyone. My name is Francisco Falcone, and I am going to be presenting the work entitled Intra-Train Wagon Wireless Channel Connectivity Analysis of Ultra-Dense Node Deployments. This is a joint work that has been done in collaboration from colleagues of Tecnologico de Monterrey, Universidad de Vigo, Deusto, and Universidad Rovira and Virgii. So the outline of my presentation is going to be the following. First, I'm going to give a brief introduction in relation with the concept of smart cities and ITS within smart cities. Later on, we will be describing the wireless channel characterization performed within the intra-train channel environment, which is the scenario under test in order to describe the operation conditions. And finally, I'm going to provide some conclusions in relation with this work. So, in order to understand the relevance in relation with wireless connectivity within the ITS, first we need to give hints in relation with the broad extended concept of a smart city. And smart cities are basically the path that is being paved in order to provide sustainable, large density urban environments, as well as providing additional services such as improving the quality of life of citizens or improving the way in which governance is implemented within these regions. Now, in order to enable smart cities as such, it is important to take into account that basically what we want to aim is to interoperate and make use of different services in order to make the environment sustainable. And in this way, we're going to be working with energy systems such as smart grids and the use of different alternative types of energies. We're going to be controlling hydric resources in order to avoid, for example, leakages and to increase the efficiency in the way in which the resource is handled. We're going to have Industry 4.0 systems in order to enhance productivity and make it more flexible and adaptable. We're going to be handling waste management, for example, in order to have an adequate recycling mechanism and classification of waste. And of course, among these, we're going to have also transportation systems. And this is the focus that we're going to have precisely in our work. Of course, in order to make these feasible within the city, we have to take into account that we must make all these systems interoperable, and also that we're going to have other type of conditions, like, for example, establishing mechanisms in order to provide open data, in order to establish open data paradigms, for example. Now, in this context, intelligent transportation systems are going to be taking advantage of different types of technology enablers. For example, Internet of Things, communication and data transfer mechanisms, as well as the use of cyber-physical systems, for example, in order to enhance the operations related with the train environments in this case. Now, wireless communications are going to play a key role in order to provide these highly interactive and flexible data exchange and control mechanisms in ITS in general, and in particular in the case of train transportation. And in the case of train transportation, it can be also foreseen in different types of environments. For example, for maintenance operations, or for example, for data exchange with passengers, or to enhance the operations in relation with what is handling the different elements within the train system, like, for example, luggage or other type of goods that should be transported as well. Now, taking into account that we are going to be working with wireless transceivers that are going to be located within the domains of the train environment, these wireless conditions in intra-train as well as in inter-train links are going to be very complex. We're going to have quite a large density of non-line of sight conditions. We're going to have interference from our users as well as from other external users and other systems. We're going to have multipath components, etc. So the goal that we are going to aim in this work is to provide the analysis of the impact in wireless channel characteristics in terms of interference as well as useful signal. In the interior environments, we're going to have large scattered densities. which is going to be applicable in this case to inter-train scenarios under test. Now, in this wireless channel characterization, we have to take into account two elements. One of them is the fact that we're going to have a myriad of systems that we can use today, spanning from public LAN mobile networks, going from 2G to 5G systems, with particular attention to those which are going to be enabling a massive IoT communications, like, for example, narrowband IoT or LTE Cat M1 and 2, as well as device-to-device connectivity within 5G. We are also going to have solutions that are going to be enabled by wireless sensor networks and wireless local area networks. And among these, there has been particular interest in recent years in terms of massive IoT communications for low-power wide area network standards such as LoRaWAN, Sigfox, or Zigbee, among others. And in the case of Wi-Fi, for IEEE 802.11ah standard in sub-1 gigahertz frequency bands. And of course, we're going to have also connectivity provided by wireless body area networks. And in this case, there's a lot of interest in relation with more compact scatter nets or wireless sensor networks enabled by Bluetooth or Bluetooth Low Energy, as well as by other more close mechanisms such as near-field communications or RFID, which can be provided for payment methods or, for example, location and tracking systems. Among these also, we have to take into account that once that we establish which is the system that we're going to use, we must comply with quality of service metrics provided by link balance analysis. And basically, what we need to understand is that our receive power levels have to be above the receiver sensitivity. And receiver sensitivity in its own time is also going to be dependent on adaptive modulation encoding schemes, the binary rates in which we are going to be working, as well as hardware constraints given by, for example, noise factors of the devices that we have. Now, we need to comply with these relations in order to provide adequate links that are going to give bit error rates that are going to be below the requirements in terms to provide the service. So it is compulsory to compute the coverage capacity requirements for each one of the cases. Now, receive power levels, as we can see, are going to be strongly dependent on physical parameters of the devices that we're going to be using, such as transmitter receiver metrics, as well as cable feeds and antenna parameters, but they're all going to be very strongly related with radio propagation phenomena. And in this case, it's compulsory to compute radio propagation. And in order to do so, there's different types of mechanisms that we can take into account, like, for example, diffraction phenomena or propagation losses with distance, or the interaction with other type of elements that are going to be within the scenario, which, for example, can be, for example, penetration losses given by certain type of materials such as walls, foliage, etc. Now, we can have alternatives that can be very accurate and that can also require very large computational time. This is going to be the case for any type of full wave electromagnetic simulation technique, such as method of moments or finite difference time domain. On the other end, we're going to have statistical empirical based methods that are going to be usually based on linear and nonlinear regression methods in order to establish an equation that is going to be valid within certain regions of operation. These are going to provide us fast results, but they're going to have to be calibrated and initially have low resolution. And as a midpoint, we're going to have deterministic based techniques, which are going to be an approximation of the full wave simulation, which are going to be based on ray tracing, ray launching, based usually on geometric optics approximation combined with uniform theory of diffraction. While this is the case, we are going to be using an in-house implemented 3D ray launching algorithm, which is going to be taken into account all of the loss mechanisms as well as diffraction and diffuse scattering. It's worth noting that we can also consider, and this is going to be compulsory, the way in which the network is established. So therefore, the materials we're going to use as well as the location and shapes of these materials are also going to be taken into consideration and are going to play a relevant role as well. So here we have the description of the scenario. Here we can see a realistic model of a train wagon implemented. And basically these are the images of the scenario which was implemented within our simulation code. We're going to be basically analyzing the way in which our system is going to be behaving, considering carrier frequencies of operation for 802.11ah, for Bluetooth Low Energy at 2.4 gigahertz, and for 5G New Radio at frequency range 1 at 3.5 gigahertz. Here are the material parameters that are going to be used inside the scenario, in which the scenario models all of the elements inside. This is basically handrails, seatings, and the materials that have been embedded, as well as the windows within the train wagon. Now, basically, once we take this model and we implement it, what we can do is we can perform wireless channel analysis by considering an arbitrary distribution of transmitters and receivers inside the scenario. Here we can see basically the case of a particular cut plane height of 1.5 meters. It's worth noting that all of the results are obtained for the whole volume of the intra-wagon train scenario, but for the sake of simplicity, we're going to only be describing it in this two-dimensional distribution. Here we can see that as a function of the transmitter location, as well as what is the operating frequency that we're going to use. You can see the distribution of received power levels are going to be varying, even despite the fact that this is a relatively small wagon scenario. However, the indoor characteristics are going to be playing a key role in the loss mechanisms that we're going to have, and later on we're going to see that also multipath propagation is going to be playing also a key role. We have also analyzed, as I said before, the impact of variations within the height of analysis, and the height of analysis is basically going to be stating which is going to be the plane that is going to be containing the receivers. And here we have two examples that are provided for different cut plane heights that are spanning from 0.5 meters up to 2 meters. Of course, 2 meters is going to be closer to where our transmitter antennas are going to be located, and this is the reason why we're going to see higher received power levels. And as we start going down, these received power levels are going to be lower. And it's interesting to know what happens when we are at 1 meter or 0.5 meters. We can see that these distributions are going to be strongly affected, and this is given by the fact of the presence of the seatings inside of the wagon. We can see that if we decrease even by a slight height the position of our receivers, we're going to have strong variations in received power levels, and we might not be able to comply with the coverage capacity requirements of the system. We have also performed analysis concerning the topological variations of the transmitter antennas, and here we see the case of modifying the hotspot location in 4 different potential antenna locations. For in the case of 5G and RFR1 at 3.5 gigahertz, again we can see that as a function of the displacement of the positions. Then of course we're going to have different distributions of the received power levels, which are not symmetrical given the fact that the scenario has different characteristics as a function of the location of the scatterers inside it. Now, in order to gain more insight, we can also obtain transmitter-receive radials instead of obtaining bidimensional current plots of the field value, and here we can use them in order to perform more detailed comparison in relation with the received power levels. And again, we can see that as a function of the height, we have variations in the received power level, and of course at a given distance from the transmitter antenna, we can see that losses are much higher, given by the fact that the links are not line of sight anymore, and they become partial line of sight or non-line of sight, with very increased coverage losses in this case. In order to gain insight in relation with the multipath propagation components within the scenario, we have also computed power delay profiles for specific locations, in this case for antenna 1 and antenna 4 that we have seen in the previous plot. And here is the example that we can see for 2 systems, 802.11ah and Bluetooth Low Energy. We can see that the variations in the echoes of the power components that are received vary as a function of the location, and they also vary as a function of which is one of the systems that we're employing. And we can see that there is a relatively large amount of multipath components that are detected, which is basically given by the fact that we have a large density of scatterers that are high dielectric or metallic, and therefore we're going to have a lot of components that are going to be reflecting on the surfaces. In the same way, for Bluetooth Low Energy, as an example in this case, we can see the delay spread estimation as a function of different cut plane heights that are spanning from 0.5 meters all the way to 2 meters. Again, we can see by varying the height, the way in which multipath propagation works is going to be, again, different. And this is mainly given by the fact that as we go lower in height, we're going to have more extension of components because they're going to be below the receiver thresholds. They're going to be absorbed. However, as we start going higher, these components are not going to be extinguished, and therefore we're going to have higher values of delay spread. And this is something that we could take into account, for example, in the design of the receivers in terms of coherence, bandwidth, and coherence time. So to conclude, basically wireless communications within this intra-train environment is going to be characterized by complex propagation conditions, even if the scenario is small, and also by variable application requirements, which might dictate where these transceivers have to be located or what is the specific protection that they're going to need in terms of the coverage capacity relations. Now, 3D RL-based deterministic wireless channel characterization validation can be employed, and it can exhibit the potential in order to accurately estimate this wireless channel behavior in frequency power as well as in time domain characteristics. And this is something interesting in order to perform system level as well as device level optimization of the wireless network planning. So this was all for the presentation. Thank you very much for your time, and I'll be open to answer any questions you might have. Thank you and have a great conference.